The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Thank you, Jan. Thank you, Farshad. As mentioned, what I want to do is I want to talk a little bit this morning about some of the work that we're looking at where we're really trying to use high-volume fly ash together with internal curing because we think that there's benefits in using both of these together. The work I'm going to present today is a combination of work from Purdue and work from NIST. We're working with Dale Bentz, and the work is really the work of Igor de la Varga, who's working on his PhD in this particular topic. The whole idea of this project is really to look at reducing the amount of clinker content per cubic yard of concrete. So for a typical bridge deck, we're looking at something around 390 kilograms per cubic meter of cementitious materials. And right now, the limits in many of the states are between 20-25% fly ash in those ranges. So our thought process behind this, and I'm not going to go through this in great detail, but our basic thought process is to start off with kind of the baseline mixtures that are used in a lot of states where we're at a 0.42 water cement ratio. We'll be looking at replacing the cement 1-to-1 with the fly ash, keeping the same volume of the overall paste in the system. And the first thing that we kept hearing from people was the issue of early strengths. And one of the ways that we can sort of come at looking at these early strengths is to alter the water to cement ratio at the early ages. So that's really what we're looking at. The matrix that we're looking at in this project, anywhere from 0 to 80% volume replacement with the fly ash. Water cement ratios from 0.45 all the way down to 0.3. This is kind of the baseline that we will typically be going back to and compare against. Now, I'm not going to spend lots and lots of time on compressive strength because I kind of have a feeling that this is a very overused property for us to be looking at. But I wanted to just mention, the whole idea is if we've got our baseline case, which is the 0.42, if we change our water cement ratio, obviously our strengths are going to go up. But if we start doing substantial replacements, either 40% replacement or 60% replacement, we could have equivalent strengths anywhere between about 1 and about 7 days with these particular materials. And in addition to just having equivalent strengths, we can really ask the question of what is the strength that we really need to be stripping form work, moving on, doing other types of construction operations. But as I mentioned, I'm not going to spend a lot of time on the strength side, but what I'm going to talk about are some of the other issues that start to come up when we start to use these lower water to cement ratios and we start to use higher volume fly ash replacements. So one of the issues that we need to be a little bit aware of is autogenous shrinkage that's going to be occurring. This is shrinkage that occurs without loss of water to the environment. This is shrinkage that occurs without a temperature change, and it happens essentially it's going to start right when the water and cement start to come into contact with each other. So the basic idea here is we need to not be using a standard test method like ASTM 157. We need to use a test method that starts earlier because this shrinkage is taking place in our lower water to cement ratio systems right from the time that the water and the cement come in contact with each other because it's really driven by the chemical reaction. So this here is the corrugated tube protocol, which recently became an ASTM standard. The idea here is you place the fresh mortar inside of the system, cap both ends of the system, and you can actually measure this while the system is fluid. We normalize all the results to be looking at these when time of set starts to occur because as soon as it starts to set, then we're going to start to build up stresses inside of the overall system. So if we look at these systems, and I'm just going to look at 4 of these systems really quickly, the basic idea here is if we had just a 0.3 water to cement ratio, we would have a substantial amount of autogenous shrinkage. And remember, this is autogenous shrinkage that's occurring if you've got perfect curing conditions, you're not losing moisture to the environment, you're not having a temperature change. We're going to be building up stresses inside the system. If you had a higher water to cement ratio, you might see a slight expansion, but then you're going to start to see some autogenous effects taking place. 40% fly ash, you're seeing what happens here. 60% fly ash, a little bit lower autogenous shrinkage early on. But the one thing that I want to point out when we look at these curves, the shape of the curve is very, very important when we're starting to look at autogenous shrinkage. If you see our conventional Portland cement mixtures, we have a substantial autogenous shrinkage that's occurring during the first couple days as we drop the water to cement ratio. That's not necessarily the case when we see these fly ash mixes, but when you look at the slope of this line, it continues out. And we've continued these tests out to 28, 90 days, and at about 21 days, these two lines will start to interact with each other. And when we stop and think about this, this kind of makes sense because we've got more reaction going on early with our plain Portland cement system. our fly ash system is reacting a little slower, but we're getting that autogenous shrinkage taking place. In addition, the thing that's important to remember is our fly ash system is going to have more chemical reaction shrinkage taking place in the system. So more chemical shrinkage, about double what we see in a normal Portland cement system, which is going to drive an increased autogenous shrinkage in these mixes. So one of the things that we really wanted to focus in on is why do we see some of these benefits at early ages in reducing the autogenous shrinkage? So one of the things that we actually do to try to quantify this is we can measure the autogenous shrinkage that's taking place inside of the system. That's what I've shown you before. Here is a measure of the internal relative humidity that's inside of these systems. So we start the test right around 12 hours, and we measure the relative humidity as a function of time. The relative humidity as a function of time is essentially telling you an indication of how much pressure is inside of the pore fluid. So here we can relate the humidity that's taking place inside of the system, or the equivalent internal humidity, with how much stress is being put on the matrix to cause this concrete to want to shrink without the loss of moisture to the outside. Again, if we've got just our 0.42 water-cement ratio, we see a lot higher relative humidity inside of our concrete, a lot less autogenous shrinkage taking place. 0.3, we see more autogenous shrinkage taking place. And then we've got here the dark symbols being the case where we're looking at the fly ash. Again, it's reacting a little bit more slowly. But in addition to that, we could go through and we could use water vapor desorption to give us another indication of some of the pore size issues. And here we can actually see the size of the pores plotted along the x-axis on a log scale, and then the size of the porosity over here. One of the things that was interesting to us is we saw a reduction in autogenous shrinkage with the fly ash simply because of the particle size distribution. So having slightly larger pores means that we can reduce the stresses that are developing inside the fluid. So as I mentioned before, the stress that's going to develop that causes the shrinkage is going to be related to essentially the surface tension of water divided by the size of the pore. So we're really interested in, one, making sure that we know what sizes of pores we're dealing with in these higher performance materials, and the second thing is making sure that we keep them full of fluid so they're not drying out and not creating this high level of stress inside the system. I won't talk about this a lot, but one of the additional benefits that we're going to see when we start looking at higher volume fly ash mixes is the increased electrical resistivity, or the increased RCPT numbers. And here you can see a pretty dramatic difference. By the time we get out to 90 days, we're looking at something with a 60% or 40% replacement, 60% being about 10 times better than we'd be seeing with our conventional bridge deck mix, about 5 or 6 times better than we're seeing with even just the 0.3 water-cement ratio material. Now, to get into the heart of what we're really trying to promote with bringing internal curing in with the concept of using higher volume fly ashes, we know that fly ash has a greater long-term chemical shrinkage. So when water and cement get together and react, they're going to undergo a volume change. 1 volume of water, 1 volume of cement get together and form about 1.84 volumes of overall reacted product. If you replace some of that cement with fly ash, you're going to double the amount of chemical shrinkage that's taking place in the system. So you're putting a bigger driver on this autogenous shrinkage that's taking place inside the system. So we have greater chemical shrinkage when we've got fly ash. We also know that the fly ash is going to take longer to react, and we have a lot of discussion about what do we need in terms of curing requirements. We also know that if we go with more dense systems, it's harder for us to get that external water. Even if we do get it on the surface, it's harder for us to get that inside of the concrete. So what the idea is behind the internal curing is to replace some of the solid particles here, which would represent sand or our aggregate, and replace those with water-filled inclusions. So those water-filled inclusions can be a variety of things. It could be a polymer that's filled with water. It could be a cellulose fiber that's filled with water. It could be lightweight aggregate particles, lightweight aggregate fines that are filled with water. The benefit of this is these water-filled particles will hold onto the water, and they'll actually absorb a little bit of water from the mix while it's mixed and while it's placed. Once the mix is set, we've essentially locked in the porosity of the system. At that point, we start to develop that underpressure in the fluid because of the chemical shrinkage that's driving this, and that actually pulls the curing water out of the lightweight aggregate. So it's really like you hear a lot of people talking about smart materials. This is kind of one of the original smart materials. Exactly when the water is needed, it's going to be pulled out of the lightweight aggregate, and it's going to allow you to have a continued hydration taking place inside of the overall system. So what I want to do here is I'm not going to go through the whole matrix again. If you're interested in more of the data, I'm happy to send you the data. But I'm going to focus in on just these two systems here where we're going to look at internal curing with 40 and 60% of the volume replacement. Now, one of the questions that comes up is how much of the water do you need to supply to the system to start to get some of these benefits? And in Dale Bentz's group, they developed an equation which really equates the supply and the demand that are needed in the system. So what we can do is we can do a simple calculation that tells us how much internal curing water do we need to supply to overcome the effects of chemical shrinkage. So we basically calculate how much cement we've got in the system, the chemical shrinkage of that cement, and the degree of hydration that that cement is going to undergo. Now remember, if we start adding fly ash to the system, we've got to add some additional terms in here where we essentially say we've got cement, the chemical shrinkage of that cement, we've got the fly ash, the chemical shrinkage of that fly ash. But this tells us how much chemical shrinkage we're going to have taking place, what's the volume, and this over here tells us, all right, how much water do we need to supply to replace that overall volume? Mass of the lightweight aggregate, the absorption of the lightweight aggregate, and then S is simply a term that tells you about the rate of absorption of the lightweight aggregate. One of the things that I will mention in here is we've tested about 18 of the commercial lightweight aggregates, and all of them have a pore size distribution that's really good at giving the water back at the right humidities and allowing us to get about a 90% efficiency. So we're giving about 90%, 92% of the water back that goes into the system to supply the internal curing. So the whole goal here is the lightweight aggregate is going to release the water when it's needed to hydrate the system. One of the big benefits is it's going to be more distributed throughout the entire cross-section, so we're not just getting the benefit up at the top where the water might be. The hypothesis is that we're going to replace all the chemical shrinkage that's taking place. Now, one of the things that we were a little bit surprised at when we started to look at some of the original data, so the little secret to the convention here is where we're adding the porous inclusions, we're going to call those the porous symbols. So here we've got the fly ash at 40% with our lightweight aggregate. And so our two green curves match up and compare with each other. The two black curves match up. So this is our 60% fly ash, 60% fly ash with internal curing. What I was surprised at is we saw a slight increase in the strength. And the reason for this, even though we're putting in a particle that may have a slightly lower strength for those internal curings, what we're getting is we're getting increased hydration taking place. So we're essentially more efficiently using the cement and the fly ash that are there because we're supplying enough water that the reaction can actually start to take place. And a way that you can actually look at that is you can see this from some of these heat curves. So these are heat generation curves from isothermal calorimetry. What we can see is obviously if we go from a 0.42 water to cement ratio to a 0.3 water to cement ratio, we're going to have differences. This difference between the 0.42 and the 0.3 water to cement ratio starts to come up because we're essentially starving the system for water. So you can't have hydration taking place, or you have a slower hydration taking place in these systems because there's not enough water in there to hydrate all the cement. If you add water on top of the cell, you'll see that the hydration rate will start to pick up again. Right? As we go from the 0.3, we'll start to see the effect of fly ash. We see that there's a slower reaction, so we see a delay in the amount of heat generation. But when you start to look at these systems here, again, same system, the only difference between the solid symbols and the open symbols is the amount of internal curing water that we're putting into the system. So when we add in internal curing water, we're seeing more hydration taking place in the system. We're more efficiently using the cement that's inside of the overall system. Right? When we look at autogenous shrinkage, we can see here that, again, this was our 0.3 before. This was our fly ash system. When we internally cure the system, we see we have a slight expansion, and then we see the autogenous shrinkage staying relatively constant and relatively low in the overall case. Now, I think this is the most important of the takeaway slides when we start to look at the real benefits of the autogenous shrinkage, or the internal curing as it relates to autogenous shrinkage. Our blue line is the stress development that's going to take place in a standard bridge deck if you don't have any temperature change or any drying shrinkage, just due to the autogenous shrinkage inside of the system. So we may have something like 150 psi after 3 weeks, 4 weeks in the inside of that system. When we look at the 0.3 water to cement ratio system, we can see that those stresses develop very, very rapidly in the system. And in some cements, if they're fine enough or if we've got finer particles, this on its own is enough to crack the overall system. Again, the shape of the curve is very important here because for the plane system, it comes up very quickly, and then as the reaction starts to cease because we don't have enough water in the system, we see this flattening out. Fly ash, though, we see this is increasing and increasing and increasing, and we see that being a linear trend, so it's going up and up and up over time. Again, this is driven because we've got more autogenous shrinkage in this case. We've got more chemical shrinkage in the case. The way we counteract this is through the internal curing water. So if we can supply that internal curing water, we can reduce the amount of self-desiccation, reduce the amount of internal drying that's taking place in the system, and keep the overall stresses low in the system. So in addition to hydrating more of the cement, we're going to get higher strengths in those systems, we're going to get reduced porosities in those systems, and we're going to build in less stress into the overall system. Now, in addition to this, one of the other benefits, and this is one of the key issues, I think, the benefit of combining our fly ash with internal curing is we can sort of take advantage of both factors here. By adding in the water into the system through internal curing, we reduce autogenous shrinkage, but the use of the fly ash helps us to monitor and maintain the temperatures that are developing in those systems is lower. So in addition to keeping those temperatures lower, what we really wanted to do is we developed something called a dual ring test. And the idea here is instead of just having a single ring, we place this concrete in between two rings, and we have the ability to change the temperature of this concrete as a function of time. So we'll place this in here. We'll actually have a water bath that controls the temperature of these rings. The rings are actually made out of a special steel that doesn't allow it to move, so the restraint doesn't change as the temperature changes. We're using INVAR. And the basic idea here, as you can see in this plot, we've got the age of the specimen plotted along the x-axis. We have the stresses that develop inside of the system plotted along the y-axis. And if we just looked at a 0.3 water to cement ratio, we essentially have autogenous stress developing in the system. And after 2 days, what we did was we subjected it to a temperature change. So we said, let's drop the temperature 10 degrees. By dropping the temperature 10 degrees, the stresses went up in the system, and it was enough to crack the overall rings. The ones where we had the fly ash and we had the fly ash with internal curing, we actually changed the temperature 30 degrees Celsius. We dropped the temperature 30 degrees Celsius and didn't see cracking in either the fly ash system or the internally cured system because you have less built-in residual stress in the overall system. And we can see that this goes out. Now, if we don't look just at 2 days, we take this out and we apply the temperature effect after 4 days, we can see that we've got some residual capacity in the plane system. The fly ash system is starting to creep up there. We've got some residual capacity, but we're now able to crack it at about a 16, 17 degrees Celsius temperature change. But the mix with internal curing, we're keeping the autogenous shrinkage low so that even when we change the temperature, we drop it from 23 degrees down to -5, we still haven't cracked the system. So this gives us additional robustness, especially at real early ages, when we're looking at stripping forms, we're looking at cold fronts coming in, we're looking at things like that. The whole idea is now we have a system that's more resistant to cracking because we've reduced the autogenous stresses out of the overall problem. As I mentioned before, in addition to just the effect on hydration of getting increased strength, we have the effect of getting reduced transport properties in these systems with internal curing. So this is just looking at a plane system, and the whole idea here is as we change our water to cement ratio on both x-axes, we can either measure the amount of water that's absorbed, or we can measure the electrical conductivity, which is very similar to an RCPT number. Plane systems are the dark dots here. All right, so as we alter the water to cement ratio, we know the system is going to get tighter. We know it's going to be harder for fluid transport in the system. But this blue dot is that the chemically replaced amount of internal curing water in the system. So even though it's mixed with a 0.3 water to cement ratio, it works like a 0.3 water to cement ratio. The benefit we get is it behaves like a 0.23 water to cement ratio in terms of allowing additional hydration, densifies the microstructure, fills in the interfacial transition zone. So there's a big benefit of this in terms of internal curing as well. So the basic idea here is we're looking at high-volume fly ashes as a way to reduce the carbon dioxide per cubic yard of concrete. The concerns for low strength, we believe, are very easily dealt with water to cement ratio and allow you to use different fillers inside of the system. We're using internal curing to more effectively use those cements when we're at lower water to cement ratios. Allows us to keep the relative humidity higher. Fly ash systems will have less initial autogenous shrinkage, but the rate of autogenous shrinkage that picks up is going to increase at later ages. So you may think, oh, well, we're out of the problem because we've gotten to 5 days and we haven't seen cracking. But remember, fly ash has more chemical shrinkage. It's taking place later in time, so we really need to be focused on what's happening at slightly later ages. We think that internal curing has the ability to reduce this autogenous shrinkage and cracking, and in addition to that, we're seeing benefits in terms of strength, but we think the real benefit is in reduced transport because we're allowing that additional hydration to take place in the system, which densifies the overall system. So with that, if there are questions.
You mentioned that the fly ash system seems to have a larger proportion of larger pores. Could you explain that? Because that seems to be a little bit counterintuitive.
We think it has to do with the pore size distribution and the particle size distribution of this particular fly ash. So what's happening is you have larger pores after 7 days because, one, you don't have as much hydration taking place, and we think it's a particle size distribution issue.
I also have a question. It's somewhat tangent, and it was also partly a question for Doug Hooton, which I'm not sure is no longer in. Oh, is there? Okay. On the RCPT results or electrical resistivity results of these high-volume fly ash, when you see a decrease in the RCPT or an increase in electrical resistivity, is it more because of densification of the system, or is it a combination of that and reduction of pore fluid conductivity because you have less pH and so on?
Yeah. So essentially your conductivity of the overall system or resistivity of the overall system is essentially a product of three things. It's a product of the pore solution conductivity, the amount of porosity, and the tortuosity of the system. When we do pore solution extractions on these, we see that it's a relatively small change in terms of the pore solution composition, and you still see those dramatic effects in terms of the densification. And in addition, for example, the water, if we go back one or two slides here, so this test may have some influence of the conductivity. So to be completely correct, we need to divide this through by the conductivity of the pore solution.
Sure.
But over here, this is simply just water absorption. Cool. So there truly is a densification of the system, and we can see this with SEM. We can see this with other measures as well. Okay. I don't know if Doug wants to counteract that, but.
No, I agree with you completely. In fact, there's a paper in CI that Michelle Knockin and I wrote a few years ago where we did bulk conductivity like you've done and related to water permeability. And then we thought, well, to be more correct, we'll actually measure the solution conductivity and correct for that. And we found that it was a very minor influence with fly ashes and slags and that. I mean, there's a small impact, but it doesn't affect the relationship very much. So I agree with you.
Thanks. Was there a quick question over there?
What type of fly ash did you use in this case, and have you looked at different types?
Yeah, we've looked at different types. This happens to be a C ash that we're using here, but we've looked at F ashes. The main difference is your replacement. The benefit that you're going to see at the different replacement levels changes, but the concept is going to be the same. The concept even works. I know Doug mentioned earlier limestones. You'll see the same concepts working with limestones, not necessarily because you're doing anything to the limestone, but you're allowing more water for the cement to hydrate, and you're taking advantage of that in the system. We can actually see, in some cases, we've actually replaced the fly ash altogether with a similarly sized inert particle, and we see similar benefits. Thank you.